Okay, so hi everyone. My name is Yacine. I am a researcher in France at University of Bordeaux. I'm doing computer science. I know that some of you have a physics background, but hopefully the talk will be accessible to anyone. It will be like high-level introduction to quantum algorithms for solving optimization problem. So I will cover the basics, and I will give you some example of tasks that we can solve with such algorithms. So maybe let me start by asking who already knows about quantum algorithm for optimization. Can you raise your hand? Okay, so not too many, so most of you will learn something, I hope. Okay, so let's start with the basics, which is what is optimization? So I think you all have an idea of what optimization is, but let's give some concrete description to all have the same thing in mind. So optimization is about finding elements that minimize a given objective. Okay, so you define an objective that you want to minimize, and you want to find the element that gives you the smallest possible value for that objective. So here I picked 3 examples of optimization. So optimization covers a lot of problems and area of research. First example is something which connects to chemistry. It is about finding the most stable configuration of a molecule. So this is an optimization problem. Another problem which connects to graph theory is about exploring a graph in the most efficient way. So you have a graph, a set of points connected with edges, and you want to find some efficient way of going around the vertices, for instance. So again, that is an optimization problem. A third example is about scheduling. So let's say you have a bunch of tasks that you want to execute on a machine. However, there is some priority, so some tasks cannot be executed before you have executed other tasks. And there is some delay and so on and so forth. So what would be the optimal amount of time that you need in order to execute all the tasks? So again, that is an optimization problem, which is very important in the industry, for instance. So there are a lot of other possible examples. Well, I picked those 3 because if you stay for the hackathon project starting next week, there are actually at least 5 projects that are connected to this kind of optimization question. Okay, so one about computing the ground state, which is related to studying the ground state of molecules. There are 2 projects around exploration of graph, one which is made with L'Oréal about finding Eulerian paths in graph, and one with IFPEN about route planning problem. And for scheduling, there are also projects with RTE and La Poste, one about electrical installation, and another one about supply of empty containers. So some of the methods that will be presented during these 2 lectures will connect to this kind of problem, and if you stay for the hackathon, you may try to use those methods when solving those projects. Okay, so let's do a slightly more mathematical definition of what optimization is. So in optimization, you have some objective function f, which maps element to, let's say, real values. And the elements have to belong to some search space, which is the space of all admissible solutions. And your goal is to minimize this function, meaning you want to find the x or the x's, there are many optimum, that minimize the function f. Okay, so if we go back to graph problem, for instance, here is a concrete optimization problem. You are given a set of points that represent like a graph configuration. And now the objective function that you may be interested in is finding a path that connects all the vertices and that has the smallest possible length. So here, the search space, omega, is going to be the set of all the possible paths that connect all the vertices. So this space is huge, like it contains exponentially many paths. I have plotted 3 possible paths at the bottom, and the function f is just returning the length of the path that you choose. And here you can see that the leftmost path is the shortest one compared to the 2 other paths. And actually, it's pretty simple to see that this is going to be the most efficient path if you want to visit all the vertices and come back to the starting point. So this is the kind of question we are interested in, okay? I'm giving you, for instance, set of points, find the shortest path. What could be an efficient algorithm for solving this task? Okay, so what's going to be the main focus of this course? So today's lecture and the next one tomorrow is to try to give some answers to the following question, which is how quantum computers may help in solving optimization problems. Okay, so we already know a lot of classical optimization methods, which are used every day by people that have to solve optimization tasks. But why should we try to use quantum computers for solving optimization tasks? Well, the first answer is because there are new types of algorithms which are based on the capabilities of quantum computers. So there are new approaches that you can follow using quantum computing and the law of quantum mechanics that cannot be done efficiently on classical computer. And of course, you hope that this new method will be more efficient compared to what is currently known. A second thing that we'll try to see is example of concrete optimization problems that can be solved with this kind of quantum algorithms. Okay, so of course, you cannot hope to have a very generic optimization algorithm that solves all optimization tasks. You have to be specific to some problem. And last thing is discussing about some benefits on limitation of those quantum algorithms compared to alternative optimization method. So this is a point we'll try to cover during the 2 lectures. Okay, let me start by giving a few definitions, so some terminology which is very often encountered in optimization and which will be used later in the course. So the first point of terminology is discrete versus continuous optimization. So this is a property about the set over which you are optimizing. So this set could be a discrete set, as was the case with finding the shortest path, meaning that you can really enumerate all the possible objects that you want to optimize on. So there is a discrete set of values that you have to explore. Another family of optimization problem is continuous optimization, where now you are optimizing over a continuous set. It could be like all the real numbers in dimension 1 or in larger dimension. Okay, so in that case, you have a continuous evolution of the function f. So there is a difference in terms of optimization method that can be used depending on what family of problem you want to solve, but there are also connections between the two. Sometimes you can reduce discrete optimization to continuous optimization, or you could discretize a continuous problem into a discrete one. A second point of terminology is about exact versus approximate solution. So when you ask for an exact solution, it means that you really want to find the best possible point, the one that really minimizes the function. So the point x star in the search space, which has the smallest possible objective. So of course, if you can do that, that is the best thing we may hope for. But sometimes it's too complicated to find the best possible point. So you could relax the goal that you want to achieve by only asking for an approximate solution, meaning that it's okay if the value that you obtain is epsilon close to the optimum. Okay, so you could have a small distance in terms of objective value between the estimate x tilde and the actual solution. Okay, so this is a kind of a relaxation, and of course, sometimes it's going to be much easier to find approximate solution compared to exact solution. And in many cases, it's okay if we only return an approximate solution. Okay, last point of terminology, it is about convex versus non-convex optimization. So this is in the context of continuous optimization. So you want to optimize a continuous function. So convex optimization is something which is very nice because the function has some very good property that will allow you to optimize it very efficiently. So I guess you all know what is a convex function, but schematically it can be represented as a graph where if you are at any point of the curve, you could see all the other points of the graph. Okay, so in some sense, wherever you are, you can see the minimum if you could look sufficiently far away. On the other hand, non-convex function could have some phenomenon like hills that give you local minima. So what is a local minima? It is something which locally looks like a minimum. Okay, so if you move away from the local minima, the function increases. However, there is something somewhere else in the function, something which is the global minima. Okay, and as you can imagine, that is much harder to optimize because you would have to look at points which may be very far from the current local optimum. Okay, so this second kind of family is much harder to optimize, but of course this is also a family which covers a lot of interesting applications. So the method that we will present will apply as well to this kind of functions. Okay, so before we start about today's topic, I would like to give a few disclaimers about quantum optimization. So the great goal of people that work on quantum optimization is to find relevant optimization problems that could be solved much more efficiently than with classical computers. So this is a long-term goal. However, we are quite far from reaching that goal. So as you will see during the lectures, quantum optimization methods, they often lack theoretical guarantees about the convergence rate, the quality of the approximate solution, and so on and so forth. Or they require making very strong assumptions about what is your optimization problem, how the solution looks like. So it is still highly heuristics. A second thing that you also should keep in mind is sometimes you have a very good quantum algorithm on paper, like you have a theoretical quantum speedup, but in practice, the speedup may vanish. In particular, because, as you know, like when it comes to implementation on a quantum computer, there are some overhead that you have to pay, like for doing quantum error correction, for instance. And these overhead are expected to be much higher than what is currently paid on classical computers. So sometimes the overhead may kind of destroy the quantum speedup at the end. Okay, and last point is like optimization is an active topic of research, and people in the classical community are still making progress, and they discover new optimization method which may actually be more efficient than what we are going to see in the lecture. Like, as you may know, like deep learning, for instance, is used in optimization now. You have stuff like AlphaFold for protein folding, which is very efficient at solving that task. So maybe quantum algorithm will not be that useful at the end. Okay, but on the positive side, the field of quantum optimization is emerging. It's a pretty recent field of research. So there are a lot of topics to explore. And the first generation of quantum computers will give us a way of experimenting even more and hopefully discover some actual application to quantum optimization algorithms. So this is a plan for the two lectures. So the goal is to present you some of the most representative technique in quantum optimization. So without going into too many details, just presenting you the high-level ideas. So today it's about physics-inspired optimization technique. Okay, so if you have a physics background, you should be able to follow that quite easily. So we'll cover both exact algorithm and more heuristics algorithms, like variational algorithms in particular. And tomorrow's lecture is more oriented towards computer scientists. This will be based on quantum algorithm that uses the property of quantum oracles. Okay, so we'll cover algorithms that are based on Grover search. We'll see how to accelerate the computation of the gradient, and then some Monte Carlo types quantum algorithms. So is there any question at that point? So feel free to interrupt if you have any question during the lecture. We'll try to go very slowly. Okay, so let's start with today's topic, which is how to solve optimization using ideas inspired by physics. So our starting point is the Hamiltonian operator, which is a very important object in quantum mechanics. This is quite a simple object. It's a linear operator. You could imagine that this is a matrix with complex entries of dimension 2 to the n by 2 to the n. And it has to be Hermitian, so the complex conjugate is equal to h. And what does it represent? It represents all the possible energy level that a system can take. Okay, so because it is Hermitian, there is something very nice, which is we can give an eigen decomposition. So decomposition into eigenvectors and eigenvalues. And the eigenvectors, denoted by ket vi, they represent the possible stationary state of your system. And the eigenvalue represents the energy levels. So they have to be real numbers because it's a Hermitian matrix. And we'll define them in order. So lambda 1 is the smallest energy, then lambda 2, lambda 3, up to lambda 2 to the n. And now you can already see why it is connected to optimization. It is because the smallest eigenvalue corresponds to the lowest energy. So this is like a minimization problem. And the corresponding eigenvector, V1, is called the ground state. And it has some physical interpretation as the most stable configuration of the system that is evolving according to the Hamiltonian H. So this is a concrete example of a Hamiltonian. So let's say your system consists of a qubit in a magnetic field. Okay, so the magnetic field is represented on the left. The Hamiltonian would be given by this 2 by 2 matrix. Okay, so in that case, there are two possible eigenvectors. One corresponds to the spin pointing up. The other one corresponds to the spin pointing down, and with corresponding eigenvalues. And the ground state, the one that has the smallest energy, is going to be the spin pointing in the opposite direction of the magnetic field. Okay, so here it's very simple. It's just a single qubit, and actually H is diagonal already, so there is not much to do to understand the system. But of course, when you start having more particles, H is going to become very complicated. Okay, so if you have n qubits, then H is of dimension 2 to the n by 2 to the n. So the size grows exponentially with the number of particles, and it may not be diagonal in the standard basis. So meaning that in general, eigenvector and eigenvalue may be very complicated to compute. Okay, so my claim is that computing the ground state, the one that has the smallest eigenvalue, is exactly an optimization problem. Okay, so I'm just rephrasing what is lambda 1 and V1. So lambda 1, the smallest eigenvalue, is equal to the norm of the state obtained by applying H on V1. Okay, so that is the Euclidean norm, the L2 norm. And this is also equal to the following optimization problem, which is you want to optimize over all the unit state in C to the 2 to the n, so all possible unit vectors. And among them, you want to find the one that minimizes the objective function, which is the norm of HV. Okay, so it's really an optimization problem. Okay, so how hard is this optimization problem to solve? Well, the first idea that comes to mind is to try to diagonalize H. Okay, because if you do that, you would obtain all the eigenvalue, all the eigenvectors, and in particular, you would obtain the smallest one. However, as I said before, the matrix is of size exponential in the size of the system. So in general, diagonalization wouldn't be efficient for solving that problem. Moreover, the optimization landscape, so if you plot the function, it is going to be something highly complicated. So it's non-convex. It could have local minima everywhere. So it will be very hard to navigate the optimization landscape of the function. So if we want to solve this kind of optimization task, we often have to make additional assumptions about the structure of H. Okay, so we don't expect H to be any possible Hamiltonian. We expect it to belong to some family of kind of easier Hamiltonian to optimize over. So let me give you some examples of kind of more friendly Hamiltonian. So this is a kind of Hamiltonian that you can expect to encounter in practice. So a first example of a very common Hamiltonian is something which is called K-local. So what does it mean? It means that you can represent H as a sum of individual Hamiltonian, H1 up to Hm. So think of M as being something small compared to the dimension. And each of the individual Hj is acting non-trivially only on a small number of qubits. Okay, so each Hj is identity everywhere, so it does nothing to most of the particles. And there is a small number of particles, let's say a constant number of them, which actually will evolve under the action of Hj. So this is something called a K-local Hamiltonian. And in practice, most Hamiltonians satisfy these kind of properties. So like in some sense, the interaction is very local and is only among a few numbers of particles. Another assumption which could be useful to make is having all the individual Hj commuting with each other. Okay, so as you know, when stuff commutes, then they will share a common eigenbasis. So it could be easier to compute eigenvalues, eigenvectors, and so on and so forth. This is a very strong assumption which usually we don't really want to make. Third assumption is being frustration-free, which means that the ground state of H is also a ground state of each individual Hamiltonian. So in some sense, the global optimum of H is also a global optimum of each individual Hj. So that is also a very interesting property when it comes to optimization. Okay, another assumption is now you look at H as a 2 to the n by 2 to the n matrix, and you put some restriction on the entries of that matrix. Yes? Does the commuting one imply the frustration? Not necessarily, I think. Well, you could imagine, for instance, that, can I write something?
Maybe say again the question.
Yes? Say again?
Say it again.
Oh, okay, so the question was, does commuting imply frustration-free, right? So I don't think so. So let's say you take H equal H1 plus H2. Okay, and H1 is just, let's say, 0, 0, and H2 is just 1, 1. Okay, so they commute with each other. But the ground state, so let's say you have a minus. So the ground state of H is 0, ket 0, right? So that is the smallest eigenvalue, minus 1. But the ground state of H2 is 1, so it does not commute. It's not frustration free. Okay, so second assumption is sparsity. So your matrix is of exponential size, but most entries are equal to 0. So meaning that you don't have to look at too many entries when you want to collect information about H. Another very important assumption, which we'll see again in a few minutes, is being stochastic, meaning that the off-diagonal term of H are non-positive real numbers. So that is a very important assumption which is going to be satisfied by some important families of Hamiltonian. Okay, last series of assumptions. Now you look at the eigendecomposition of H, and you may put some restriction on how this eigenspectrum looks like. So one is being non-degenerate, meaning that there is a unique smallest eigenvalue lambda 1. Okay, so there is a unique ground state associated to the smallest eigenvalue. Okay, and last assumption is something even stronger, which is that actually there is a large gap between the smallest and the second smallest eigenvalue. Okay, so on that assumption, the gapped assumption is also extremely important, and we'll use it for the algorithm that we'll see in a moment. Okay, so the point I want to make by describing all those kind of assumptions is that optimization is often about making the right set of assumptions in order to give some non-trivial quantum algorithm. But on the other hand, if you make too many assumptions, then the problem could become classically easy as well. Okay, so this is an example. Okay, I forgot the last one, but it's not very important. So let's imagine that you try to optimize, so find the ground state of a Hamiltonian which is k-local, stochastic, and frustration-free. Well, it turned out that this particular set of assumptions actually makes the problem classically easy as well. Okay, so it's a very subtle way of doing, so you shouldn't make too many assumptions, right? It's really all about finding the right set of assumptions which makes the question non-trivial. Okay, so why do we care about computing the ground state? Well, maybe the most important reason is because the ground state has some physical meaning. It gives information about the electronic configuration, phases of matter. So it is used in many areas of research, such as quantum chemistry and so on and so forth. But also because, as you will see, there is a lot of other optimization problems which can actually be viewed as optimizing, finding the ground state of a Hamiltonian. So it really covers a lot of optimization tasks. So I would like to give you one concrete example of something which at first may not look like Hamiltonian problem, but you'll see that it can actually be phrased as computing a ground state. And this is going to be related to combinatorial optimization. So this is a problem. This is called max cut. It's a very famous problem, which is studied in combinatorial optimization. So again, it's going to be a graph problem. So the input is a graph. so vertices connected by edges. And now your goal is to minimize the following quantity. So you want to partition the vertices into two parts, which are disjoint from each other. And you want to minimize the number of edges that goes from one side of the partition to the other side. Okay, so on this example, the cut on the left is represented by the bold edge and is of size 6 because it crosses 6 edges. Okay? Another cut on the right is of value only 3 because it cuts only 3 edges. So max cut is about finding the cut that will like cross as many edges as possible. So as I said, this is a fundamental problem in discrete optimization and combinatorial optimization, but at the same time, it's also an extremely hard problem to solve. Okay, so it's actually NP hard, even if you want to approximate it with very small precision. So there is a very famous classical algorithm that can approximate the solution up to a certain point, which is called the Gemans-Williamson algorithm. I mean, I can only encourage you to look at that algorithm because it's a very nice result. And there is like a large theory which is built around this approximation complexity of max cuts. So people have tried to see if quantum computers may provide better approximation to the max cut problem compared to like existing classical algorithms. So how could you solve it using Hamiltonians? So let's do it step by step. I will show you how to construct the Hamiltonian. So what we'll do is we'll introduce binary variables, one for each vertex of the graph. So here we have 8 vertices and variables x1 up to x8. Okay, so for simplicity, I'm assuming that they take value +1, -1, okay, instead of 0, 1. Now, max cut can equivalently be defined as the following thing. You want to minimize over all possible assignment to the vertices the following objective, which is a sum over all edges of -1/4 xi minus xj square. Okay, so why does it represent the correct objective function? Well, you can see that if two vertices belong to the same side of the partition, then xi minus xj would be equal to 0. And if they belong to different sides of the partition, then the quantity would be equal to -1. Okay, so finding the optimum assignment to the variable xi's correspond exactly to finding the size of the maximum cut. Okay, so we just rephrased max cut as optimizing a quadratic function with binary variables. Now it's quite easy to encode this objective into a Hamiltonian. So how would you do that? Well, you would take H to be a diagonal Hamiltonian, so it is 0 everywhere except on the diagonal. And on the diagonal, what you have is the value of f of x. So f of x is the objective function, and the entries correspond to the assignment of x to a particular set of +1, -1 values. Okay, so it's completely straightforward in some sense. I mean, you are just putting all the possible outcome on the diagonal, and of course, the smallest one will correspond to the ground state of H. So it turned out that such a Hamiltonian is actually pretty well known. It's called an Ising Hamiltonian, and it can equivalently be written in the following way, which is a sum of Pauli Z matrices. Okay, so by Zi, so Zi is just a tensor product of identity. except the matrix Z. So okay, so it's a simple exercise to prove that the two matrices, like the two representations, give rise to the same matrix, just using the Pauli Z matrix acted on the highest qubit of the system. Okay, so what does it show? It shows that if you want to solve max cut, well, you could just consider that particular Hamiltonian and just try to find its ground state. And if you could do it efficiently, well, you would have a solution to the max cut problem. So actually, this kind of Hamiltonian encoding is a very general way of performing optimization. It turned out that there is a large family of problems which can be encoded that way. This is all the so-called QUBO problems. So you want to minimize some quadratic polynomial which is given by some symmetric matrix Q. And if you just replace the variables with the right Pauli matrix, then the ground state would actually give you the ground state of, would give you actually the minimum state of your QUBO problem. Okay, so there have been papers that tried to kind of rephrase optimization problem into such kind of Hamiltonian. And like if you look at this reference, for instance, it gives a lot of NP problems in particular for which you can really rephrase the problem as finding the ground state of a particular Hamiltonian. Okay, so it really shows that Hamiltonian can capture a lot of optimization tasks. Okay, of course, there is a limitation about this approach, which is that in general, there is no guarantee that the resulting Hamiltonian is nice. Okay, so before I listed a few properties which can be satisfied by Hamiltonians, and I mean, most of those properties are not satisfied by this kind of QUBO Hamiltonian. So in particular, the spectral gap is often very small or unknown. There could be interaction between qubits at a very long distance. There could be a very high dimension, a lot of ancilla qubit to be used in the reduction. So it is a promising approach, but still the resulting Hamiltonian in general doesn't have very good properties. So the question is really, can we find at least some inputs to those problems for which we can show that H will have some desirable properties? Yep.
I wanted to understand why the small spectral gap can be a challenge. Why can it pose a challenge to
Maybe for people online.
Yeah, so, say again?
Can you tell it again for people online?
Yeah, so the question was about why should we assume that the spectral gap is large, right? So you'll see in a minute. So I will describe optimization algorithm that depends on how large the spectral gap is. So the larger the gap is, the more the algorithm will be efficient. Okay, so the complexity will depend on the largeness of the spectral gap. Okay, but you'll see in a minute why it comes into the picture. Okay, so we have motivated why the ground state is something which is interesting to compute. Now, yep, please go.
Can I just follow on the question? Is it also the gap will affect the fact that when you do computation, your initial state has to be kind of good approximation, and it cannot have directions into the other states that you're interested in the ground state? It has to have an overlap with the ground state?
Okay, so the question is about connection between the spectral gap and the initial overlap of the starting state with ground state, right? So I will also answer this question in a minute, okay? But it's not directly related. Okay, so now we would like to solve this problem using quantum computers. So what could we do? Like, how a quantum computer may be helpful in computing the ground state. So there is one task for which quantum computers are very good at, which is doing the following thing, which is called Hamiltonian simulation. And essentially, it is about solving the Schrödinger equation. Okay, so if you have a Hamiltonian H, and you want to know how the state of your system is evolving in time according to H, then the evolution is dictated by the Schrödinger equation, which is an equation which is very hard to solve on a classical computer. But actually, if you have a quantum computer, and if H is not too bad, then you can actually solve the Schrödinger equation and compute a state psi1 which corresponds to evolving the system for 1 unit of time. Okay, so this was the original grand goal of quantum computers, which were identified by Feynman originally. Like he said, if you want to simulate the evolution of a quantum systems, then you should better use a quantum computers. And indeed, we have discovered plenty of algorithms that can do such a simulation in a very short amount of time. So for the rest of the talk, maybe you should keep in mind this notation, CIMH, which is the time it costs to simulate H for 1 unit of time. Okay, and think of it as being something very small, okay, like polynomial in the size of the system. So of course, simulation is nice, but you may ask, what is the connection with optimization? Okay, so we know how to simulate H, but what does it say about computing the ground state? How to connect the two tasks? So next part is going to be exactly about answering that question, like connecting simulation with optimization. And for that, we'll look at 2 optimization algorithms. One is quantum phase estimation, and the second one is the adiabatic algorithm. Okay, is there any question before I move to the next section? Okay, good. So let's start with our first quantum optimization algorithm. So it's exact because, as you'll see, it can exactly compute the ground state. It's not an approximation algorithm.
Even for the n-part problem?
Say again?
Even it gives the exact solution even for the n-part problem?
For which problem?
NP-hard.
The question is, does it give the exact solution even for NP-hard problem? So the answer is yes, but the running time can be exponential, right? So, okay, this is just what I said. So quantum phase estimation. So I think Thomas will give you more detail about what is quantum phase estimation. I'm just giving a high-level description of what this algorithm is doing. So quantum phase estimation is a very famous quantum algorithm for computing eigenvalues, like energies of a system. And it's pretty simple to describe. So the input is an eigenvector Vi of H. There is a bunch of ancilla. And what you do is you will use Hamiltonian simulation with different parameters for the time evolution. So you see, like, you are making an evolution with 1 unit of time, then 2 units of time, 4 units of time, etc. And at the end, you apply an inverse quantum Fourier transform. Okay, so I'm not going to make the analysis of this quantum circuit, just giving you the final outcome. So the first register is going to be unchanged. It just remains an eigenvector. Now the second register, the second family of registers is where the magic happens, because at the end, if you measure it, then with very high probability, you will compute something which is a binary encoding of lambda I. So the eigenvalue associated to VI. Okay, and this is up to a precision epsilon, which depends on how much time you want to spend in doing the Hamiltonian simulation. Okay, so this is really an algorithm for computing eigenvalue. Okay, kind of an alternative to diagonalization, for instance. And so what is the cost of the algorithm? Well, so the cost is how many quantum gates, so what is the size of the quantum circuit? Well, essentially, it is going to be 1 over epsilon. Okay, so the smaller epsilon is, the more expensive it is going to be, multiplied by the cost of simulating H. Okay, so as I said before, this cost is usually polynomial in the size of, or polynomial on the size of the system. Okay, so now we can see, I will explain why the spectral gap assumption is important, okay, because we have not computed the ground state yet. So to explain why the spectral gap is important in the picture, we can have the following thing in mind. So here I've plotted the energy level of H by increasing order of magnitude. Okay, so the lowest eigenvalue, lambda 1, is at the bottom, and then you have the excited states on the top. And assume that there is a spectral gap between lambda 1 and lambda 2. Now what it implies is if you want to distinguish lambda 1 from the other eigenvalues, then the precision of the estimation in quantum phase estimation, epsilon, has to be smaller than delta. Okay, because as I showed before, the output is precise up to an error epsilon. So the error should be sufficiently small such that lambda 1 and lambda 2 are separated by something which is smaller than the gap between the two. So the closer they are from each other, the higher the precision should be if you want to distinguish between the two eigenvalues. So now there is an issue that we also have to address, which is how to come up with the input of quantum phase estimation. Okay, so it computes the eigenvalues, but you have to put the eigenvectors as input. So how to come up with candidate eigenvectors. So this is a big issue, and what we can do is to use something which is called sometimes a warm start, which is a state that has the best possible overlap with the ground state. So this corresponds to what was the question a minute before. So let me give you the full algorithm, and you'll see how it works. So there are essentially 3 steps. First one is you have to come up with a warm start, which is just any state of your choice. Okay, so here it is written in the eigenbasis of H, and the amplitude alpha 1 up to alpha 2 to the n, they depend on which state you have chosen. Then what we do is we run quantum phase estimation on that state, so it will estimate the eigenvalue in superposition up to a precision delta, which is sufficient to distinguish lambda 1 from the other eigenvalues. And then what we do at the end is either we measure the state, and we hope that it will collapse to the smallest eigenvalue, or we could also use something called amplitude amplification, which will amplify the amplitude of the lowest eigenvalue. Okay, so this is a standard amplification technique. So what is the cost of this algorithm? Well, there is on the right the cost of performing phase estimation, and on the left there is the cost of how close the warm start is from the actual ground state. Okay, so in the best case, the warm start is exactly equal to V1, so the overlap is 1, and you just have to check that it is indeed the ground state by doing phase estimation. If it is very far from the ground state, then you will have to amplify it a lot, and you will pay a large factor that depends on the overlap. So you can see that the overlap does not really depend on the spectral gap. It's really a property of how good you can guess what should be the ground state. Okay, so a few comments about this quantum optimization algorithm. On the positive side, it provides the exact ground state, so it's not an approximation. And the algorithm requires relatively few assumptions about H. Essentially, we needed to have a large spectral gap, and we want H to be simulatable in an efficient way. Now, there are important limitations. One is phase estimation is something which is very expensive to do in practice. The circuit is pretty large. You have to do quantum Fourier transform, so this is not something you could do on a near-term quantum computer. You would also need to do error correction and so on and so forth. And the last limitation, maybe this is the most important one, the algorithm requires a very good warm start. So you want the overlap to be as close to 1 as possible, which very often is very hard to achieve. Like if you have no idea about the optimum and you just pick a random warm start, then the overlap could be exponentially small in the size of the system. So the next part, the next quantum algorithm will try to address the last limitation. We will try to kind of avoid making this assumption about having a good warm start to initialize the algorithm. Okay, so next algorithm is the adiabatic one. So it's a very famous optimization algorithm, something that will allow us to bypass the warm start assumption. So the basic idea of the adiabatic algorithm is the following observation, which is relatively straightforward. Let's say you have H0, that is some initial Hamiltonian, and you just change it by a small amount. Okay, so you make a small perturbation on H0. Well, then you would expect that the ground state of H0 is kind of very close to the ground state of the perturbed Hamiltonian. Now it suggests a bootstrapping ID for finding the ground state of any Hamiltonian, which would do the following thing. So assume that you know the ground state of H0, and you use it as a warm start for finding the ground state of H0 plus delta H1. Okay, so because of the small perturbation, it's not exactly the ground state, but the overlap will be very close to 1. So that is a very good warm start. Okay, so you could just prepare V1, use it as a warm start to prepare W1, the next ground state. And then you could repeat. So you do one more step of perturbation. You use W1 as a warm start to prepare the ground state of the next Hamiltonian. So you see that if you do that, you could explore a sequence of slowly changing Hamiltonian, and by doing that, you could arrive at your final target Hamiltonian in a very efficient way, I mean, without needing to know a warm start from scratch. So let's try to formalize this idea. So what the adiabatic theorem says is if you have a system which is initialized in the ground state of a time-dependent Hamiltonian, and if the Hamiltonian evolves slowly enough, then the state will remain the ground state of the current Hamiltonian at all time. Okay, so just to give you a picture, let's say you have a magnet and you are making it move slowly to the right, well, they will just stay aligned, right? But if you evolve it very quickly, then they may not be aligned anymore. So let's give a mathematical statement of this phenomenon. That is a Schrödinger equation in which I introduce an extra parameter v, which is a scalar number between 0 and 1, and it is going to control the speed of the evolution. So the smaller v is, the less the Hamiltonian will evolve in time. Okay, so now this is a time-dependent Hamiltonian, which is an object which is more complicated to study. Like the eigenvalues and the eigenvectors will also evolve over time. And in general, the Schrödinger equation has no analytical solution. Okay, so it's more complicated to analyze than time-independent Hamiltonian. So just to give you an idea of what the evolution could look like. So here I have plotted the eigenvalues as a function of the time. So initially, we have some distribution of the energy level. Okay, and then we make the time increase. So h is going to change, and the eigenvalue will also change as well. Okay, so the eigenvectors will also change, but we mostly care about what happened to the eigenvalues. Now, this important quantity is going to be the spectral gap at the worst possible step of the evolution. Okay, so instead of just at a fixed time step, delta is now defined as like the closest distance to which lambda 1 and lambda 2 can be over the entire evolution. And the important assumption is that there is no level crossings, meaning that delta remains non-zero all along the evolution. Okay, so it's kind of, as before, this is like the spectral gap assumption. Okay, so this is the actual definition of delta. And now this is a mathematical statement of the adiabatic theorem. So it says that if the initial solution psi naught is the ground state of h at time 0, and if you choose the speed to be sufficiently small compared to delta, okay, so the exact expression is delta square times some other terms, then if you solve the Schrödinger equation using such a value for v, then psi1, the state at the end of the evolution, will be epsilon close to the ground state of the final Hamiltonian. Okay, so the psi t will remain equal to the ground state throughout the evolution. And now the cost, as you can see, it no longer depends on the overlap of a warm start with the ground state. Now the cost depends only on the simulation cost of h and how small the parameter v has to be. And if you can show that delta is quite large, then the entire cost could be much better than the one you would have using quantum phase estimation. Is there any question about the adiabatic theorem? Yep.
How can we use adiabatic theorem for the stochastic problem?
Okay, so the question is, how can we use adiabatic theorem for a stochastic problem, which again is something I will answer in a minute. So that is applying the adiabatic theorem. So let's say you want to apply it to a stochastic Hamiltonian and something, let's say a cubo Hamiltonian. So like that is the Hamiltonian that we have for the max cut problem. So how would you use it in the adiabatic theorem? So first thing is you have some target Hamiltonian in mind. So this is the one that you want to, for which you want to find the ground state. So this is your final objective. Now what you will typically do is you will choose another Hamiltonian h naught, which is one for which it's very easy to prepare the ground state, something which is very easy to optimize. So one example is the so-called transverse field Hamiltonian, which is just a sum of Pauli X matrices. Okay, the ground state here is just the uniform superposition over all states. Okay, so the ground state can be prepared very easily for h naught. Now, final step is to define ht. So that is the Hamiltonian on which we'll apply the adiabatic theorem. And we want ht to be an interpolation between h0 and h1. Okay, so at the beginning, it is equal to h0, the easy Hamiltonian, and at the end, it has to be equal to h1. So you can choose how you want to interpolate, but a typical choice is to use the so-called line interpolation, which consists of having 1 minus th0 plus th1. Okay, so you just have a linear increase in the contribution of h1 to the overall Hamiltonian. Now, what kind of requirement do you want? Well, first, h0 and h1, they should not commute, or you would have level crossings, so the gap would be closed. Second important condition is the spectral gap is expected to be as large as possible because the evolution speed depends on how large delta is. So this is going to be the main issue. I mean, in general, it's hard to say anything about how large delta is. And last requirement, ht has to be efficiently simulatable using Hamiltonian simulation. So let me say a few words about this caveat. So first one, I already mentioned it. In general, when applying the adiabatic theorem, it is hard to say anything about the spectral gap. Well, if it is extremely small, then the evolution will take a lot of time and the algorithm will not be efficient. A second limitation of the adiabatic theorem is that the choice of the time-dependent Hamiltonian is constrained by the type of quantum architectures on which you want to solve the adiabatic theorem, on which you want to run the Hamiltonian simulation. So an example is like Rydberg atom, which is a typical choice explored by some companies for doing analog computing and solving this kind of optimization problem. The issue is there are some restrictions on the type of interaction that you can have in HT over time. Okay, and if you don't have the right interaction, then the cost may increase a lot if you want to do the simulation. Okay, and the last limitation of the adiabatic algorithm is, again, it is not very efficient if you want to use a near-term quantum computer. Okay, I mean, as we have seen, you have to evolve a quantum state for a certain amount of time, so you have to preserve coherence all along the evolution. You have to correct quantum errors, etc. So this is not very well adapted to near-term architectures. So the next section will be dedicated to kind of addressing the last point and giving you some example of other algorithms that could be applied on near-term quantum computers. Okay, so before concluding this section, well, you may ask, there are a lot of limitations. Maybe in practice it's impossible to use the adiabatic algorithm. So maybe the spectral gap is always very close to zero, extremely small. Maybe it's not even efficient for any problem of interest. So this is something which is investigated a lot by the research community. And there are some examples of Hamiltonian which are close to what we saw before. In particular, there are stochastic Hamiltonian, for which it has been proved mathematically that the adiabatic algorithm would be almost exponentially faster than any classical optimization method. Okay, so it's like a provable result about the superiority of this algorithm on certain kinds of Hamiltonians. So there is some hope that it could be interesting to use this kind of technique on the long term to solve some concrete optimization problems. Okay. Any question about this? I think it's going to be heuristic in that case. So yeah, you could test the value of the final solution and then try to optimize with like a lower velocity. Or you could have some estimate about what the velocity could be in advance and use it, plug it into the algorithm. But yeah, in general, it's very hard to know how close the gap is going to be. Yes?
How far to generate the matrix H0 so that doesn't commute with H1?
Say again?
How far does it generate H0 so it doesn't commute with H1? Because it can be big.
The question is, how hard is it to find H0 that does not commute with H1? But that is not very complicated. In general, you can, like here it was quite obvious. Like one was in the Z basis, the other one in the X basis. In general, I don't know, like if you take two matrices, they will not commute with high probability with each other. So this is not the strongest requirement. What is hard is to find H0 that will not make the gap being exponentially small, for instance. This is much harder to satisfy. Yeah, it's more the gap. Like the gap is something even more than just not commuting. Yes?
Do you have any formulation to approximate the energy gap so it's not associated beforehand?
So the question is about how to estimate the energy gap. In general, there is no technique. Like, well, this is a very hard question, actually. So it's a case-by-case analysis in general. Okay, so last part is about variational methods. So this is a huge family of quantum algorithms which are much more heuristics and which may give you approximate solution. But on the positive side, they could be much faster than what we studied so far. So the main idea of variational algorithm is to reduce the search space for the ground state to a smaller region which can efficiently be explored by combining classical and quantum algorithm. So it's going to be a hybrid method. So we'll not try to find the optimum over the entire search space, but only a small region of the search space. So let's start with the variational quantum eigensolver. So we are back to the optimization problem for Hamiltonian. And well, you may ask, why don't we try to use classical optimization method? Okay, before using quantum one, why don't we use classical one? And well, there are some obstacles that you immediately face. One is the search space is extremely large, right? You want to optimize over vectors of dimension 2 to the n. So you have exponentially many parameters. So even storing the state on your memory would not be possible to do. A second limitation is the objective function is also very hard to evaluate. Okay, so even if V is a very simple vector, something very sparse, for instance, then you would like to multiply it with a matrix which is of exponential size. So this could also not be possible to evaluate on a classical computer. So you see, even the basic of just storing the state and evaluating the objective function is already too complicated. Okay, so it's not even about optimization, it's already complicated to manipulate the objects. Okay, and the variational method is kind of a way of addressing this issue by using a hybrid approach. So this is how it works. On the classical side, so you have a classical computer, let's say a supercomputer, and the classical computer is going to select a candidate that has a concise classical description. Okay, so it will select one candidate state that is not too difficult to describe. And it will send the description to the quantum computer. Now the quantum computer will construct the quantum state that corresponds to the description, and it will evaluate the objective function and return the value to the classical optimizer. Okay, and the classical optimizer is expected to improve the solution depending on what was the value of the objective function on V. Okay, so it's really an iterative process. So one of the big advantage of the variational approach is it could require much fewer quantum resources compared to the algorithm we studied before, because now the quantum algorithm is just used to estimate the energy and nothing else. So this is a leading proposal for near-term quantum computing, and it's actually being tested in practice. So for instance, in France, there is a project about combining some supercomputer with some near-term quantum computers to try to address some kind of hybrid variational methods. At the same time, it is highly heuristic, but well, so is classical optimization on such problems, so that could be okay if we can find interesting solution with this approach. So this is just a high-level description. So now let's try to go into the details. And the important question to address is what should be the concise description of a candidate state? Okay, so how to represent such a state? So this is going to be about finding what is called an ansatz. So an ansatz is a mapping from classical parameters that have been chosen by the classical optimizer to a particular quantum state which is going to be constructed and evaluated on the quantum computer. Okay, and of course you want to have as few classical parameters as possible for the method to be efficient. So what we'll see in the next part is one particular example of an ansatz, which is called the QAOA ansatz. Okay, so before that, there's just a remark. So the quantum computer could estimate the energy using quantum phase estimation, as we said before, but that wouldn't be efficient if we want to use near-term quantum computers. So typically, you can instead use some random measurement strategies. So you would just do repeated random sampling, and you can average the result, and it would give you something that approximates the objective function. Okay, so before describing what is the ansatz used in QAOA, as I said, the choice of the ansatz is really the crucial step in using the variational method. However, there is a very important phenomenon to have in mind, which is called Barren plateau, and which is an important limitation to the variational method. So it says the following thing. I mean, you may try to use very expressive ansatz, so like quantum states that explore a large region of the search space. But if you do that, because of some property in high dimension, the classical optimizer would have a very high chance of getting stuck in local minima. So let me give you like a mathematical statement of this phenomenon. So you have an observable H, so this is the Hamiltonian. Then there is a statement that says that almost all the states in your universe have an energy which is almost always the same. Okay, so there is not a huge variation in terms of energy. So most of the landscape is almost flat. Okay, so if the ansatz is exploring a lot of states, like a large part of your entire region, then it is very likely to get stuck on this kind of very flat region of the landscape. So it means that finding the good ansatz is a very hard question, actually. If you don't define it the right way, then the overall method may be failing because of this kind of phenomenon. Okay, so let's go to a concrete description of one particular ansatz, the QAOA ansatz. So the main message is that we are going to define an ansatz which is inspired by the adiabatic algorithm. Okay, so we will use the ideas developed in the adiabatic algorithm to define what a plausible ansatz could look like. Okay, so a reminder, the adiabatic algorithm is about solving the Schrödinger equation for a time-dependent Hamiltonian. And the goal is to understand what the final ground state should look like. Okay, and if we understand the structure of the ground state, then maybe it will tell us how we should pick the classical parameters and how we should define the mapping to a quantum state. So first idea is to discretize the adiabatic algorithm. So this is a standard idea. Instead of a continuous time evolution, what we'll do is we'll approximate the evolution of HT by a sequence of slowly evolving Hamiltonian. This is something we already discussed before. So H0, then H delta, etc., for a sufficiently small time step delta. Now, if we solve the Schrödinger equation for each individual Hamiltonian, then we can easily prove that the ground state is actually equal to the product of the unitary evolution for each of the individual Hamiltonian when delta goes to 0. Okay, so if delta is very close to 0, this will exactly return the same state as if we solve the original time-dependent equation. Okay, so I just put it back, the equation. Now, suppose HT is given by the line interpolation. So this was one possible choice, interpolating between H0, the easy Hamiltonian, and H1, the target Hamiltonian. So now we would like to understand how each unitary behaves. Okay, so let's just focus on one of them, the JS1. So we can replace Hj delta by the corresponding equation given by the line interpolation. And we would like to kind of simplify this unitary, like give another expression. So maybe you may suggest to do the following thing, which you would do if it was defined over the reals, which is just split it into two exponential. Okay, so this is not possible. Like, if you have non-commuting matrices, this is not correct in general. What is correct is the following thing. This is called the Trotter approximation formula. And it tells you that the exponential of a sum is going to be equal to the product of each individual exponential that you have to alternate many times. So there is a parameter delta prime, which tells us how long we should evolve according to H1 before moving to H0. Okay, and we have to repeat this 1 over delta times. And if delta prime goes to 0, then this is equal to the initial exponential, matrix exponential. Okay, so if we put everything together, this is what we have. So the adiabatic algorithm could equivalently be written as the following circuit, which correspond of alternating between two kinds of unitaries. Okay, so the ground state psi1, it applies H1 for a certain amount of time, then H0, H1, H0, and so on and so forth. So this is the result. For any epsilon, now I'm replacing delta and delta prime by epsilon. For any epsilon, there exists a depth. So how many times you want to alternate, and a sequence of angles, such that the ground state can be written as the following state. Okay, so we have obtained an expression for the ground state of the Hamiltonian. And this will tell us what the ansatz could be. So the QAOA ansatz is just taking the same kind of state, but now it will try to guess what are the angles. So we kind of do the opposite. Now the angles and the number of angles is going to be chosen by the classical optimizer, and the quantum algorithm will evaluate the ansatz and return the energy. And the hope is that there exists sequence of angles and depths which could be more efficient than just using the adiabatic algorithm. So maybe there is a way of compressing the evolution in some sense, kind of finding shortcuts in the evolution of the adiabatic algorithm. So maybe you may think it's nonsense, but actually, the advantage is to have circuits of lower depth, but actually it has been shown that even with p equal 1, so just one alternation between h1 and h0, there is already some non-trivial phenomenon that occurs in terms of what is the return state. So, for instance, the corresponding state that we obtain at the end with this kind of ansatz is giving you some good approximation to some Hamiltonian, and it has also some improvement in terms of what kind of distribution it can generate. So there are some provable statements about the quality of this kind of ansatz, but the difficulty is that provable speedups remain difficult to prove, and when p is larger than 1, it becomes even harder to analyze theoretically how good the ansatz could be. Okay, so we'll finish here. So just a recap. So today we covered the part on the left. So we look at optimization as a ground state computation problem. So we saw that there were a lot of problems that could be phrased that way, and we gave 4 algorithms for which the ground state could be computed either exactly or using some heuristic approach. Okay, and tomorrow we'll look at a completely different family of algorithms which are based on quantum oracles. Okay, so I will stop here. Thank you.
Okay, so the timing perfect. Like this, we have time for questions. So if you have some questions, just let us know. Yes? I can answer.
Thank you very much for the presentation. My question was regarding the using those quantum algorithms to solve an optimization problem. Most of the time, the optimization problem is formulated as a Kubo, because then we can write it as a Ising Hamiltonian. Are there any other Hamiltonians that are suitable for solving optimization problem that come from combinatorial problem to escape this routine?
Yeah, not that I'm aware of. Yeah, I mean, typically this kind of reduction from combinatorial optimization to Hamiltonian is producing something which is diagonal in the standard basis, right? So I think that's why Ising Hamiltonian are sufficient in general. Yeah, I don't think there are cases in which you would generate more complicated Hamiltonian.
Thank you. So I have a question, because the idea of the adiabatic computation comes from the very old idea of homotopy, so path following in other fields. And of course we are dealing here with Hamiltonians, which are nice and Hermitian. But the homotopy methods can be extended beyond that when we can start from a nice, for example, Hermitian problem and then approach the non-Hermitian. Are there any attempts in that direction in the quantum setup?
So you mean you would like to optimize non-Hermitian matrices? That's a good question. I don't have the answer, actually. I think one limitation is you need to be able to simulate the dynamic, right? So if it's not Hermitian, I don't know how far you can go in terms of simulation on a quantum computer, I mean.
Is there other questions?
So there is a question online, which is, what are the today's limitations of these methods?
What are the limitations? Well, I gave some answer to this question, I think, during the talk. I would say the first family is kind of require large-scale quantum computers, so like quantum machine of very good quality. The second family of method, we may hope to be able to use them on near-term quantum device. They may be less guaranteed in terms of how good they perform. So it's kind of, yeah. But right now, the existing quantum computers, they are still not allowing us to test any of those methods. Yeah, it's still like advanced quantum algorithm in some sense.
Okay, if there is no other questions, so let's thank Yassine again.